So last time we basically proved the Poisson formula, right? So we said the following. So let me write two Poisson formula, one for parabolic function. So if f is a parabolic function, so let's write fn parabolic. Remember what a parabolic means. Bounded parabolic, sorry, bounded. It's very important here. Bounded parabolic function. So there's a correspondence between bounded parabolic functions and tail and bounded tail random variables. Okay? So bounded parabolic function, right? So let's call this f, and then we can define L. So here we would need a real valued or to define lim sup properly, okay? So I'm going to define LF to be the lim sup as t goes to infinity of f of xt. Okay, now what do I mean by this? This is a complex valued object. So you just take the real part, you take its lim sup, and you take the imaginary part and take the lim sup as well for the imaginary part. Okay, let's just linearize the lim sup. But that's what I mean by this thing. Or you could work in linear, or you can work in real valued. You can check that a parabolic function, a function is parabolic if and only if its real part and its imaginary part are both parabolic. So it's the same thing to work on only in real valued functions. Then the lim sup is well defined, and then you can get the Poisson formula for the complex valued case just from the real valued case. Okay, so then this is bounded, of course, by definition, tail measurable random variable. And the converse is also true for any bounded tail measurable random variable L. There exists well, okay, we can do, okay, so there exists FL, which is a parabolic function, bounded, again, I forget the bounded parabolic function. And in fact, we already saw how to get this FL, right? We get this FL by defining FL of x and t. We define it to be the expectation starting from x of LT theta t, where, right, sorry, LT, right? Of LT, where LT composite theta t is L, right? So either you have these random variables which give you L, and these are converses of each other, right? So I'll write it shorthand L, F, L is L almost surely, EX for every X, and F, L is F. Sorry, FLF is F, right? So if you start with an F and you do it, you go back and forth, you get back to the same F. If you start with an L and you go back and forth, you get back to the same L, okay? And, okay, so this is the Poisson formula. And if you're thinking of why is this the Poisson formula, in a certain sense, it tells you that if you have that the t measure random variables, there are these boundary points, okay? So you can think of the t measure of random variables, bounded t measure of random variables, you need to think of them as L infinity of some space. So if you put boundary values on that space, which is basically specifying an L infinity function, then it uniquely extends to a parabolic function. Okay. Now, the only thing we didn't prove, we proved everything here. There's one thing that I kind of messed up in the middle of the proof, and that was to prove that this is actually, that when you define this, you actually get a tail measurable object. Okay, so we'll do that in a second, but let me write the other Poisson formula. So this is the parabolic case. And the harmonic case is the same exact thing. And this I leave for you as an exercise, okay? So if H is a bounded harmonic function, then we can define LH to be the lim sup of H of xt. Okay. Again, these lim sups, by the way, these are martingales, right? So the limits exist almost surely, but I want a well-defined function, random variable, so I just define it to be the lim sup. It's almost surely equal to the limit. Okay. So LH, this is a bounded invariant random variable. And the converse is also true for any bounded invariant measurable on the variable L. The function, now I can actually define it without even appealing to any with any shifts or anything, just to define the expectation of L is a bounded harmonic function.
This is just an application of the parabola. So then the harmonic function is up, and then we just need.
You have to be careful. You have to be careful because here it's I measurable and here it's T measurable.
Justify
why. There are some directions you can use this one, yes. Okay, but some directions, the other direction to go, you have to. This is stricter, right? Because I is smaller.
Yeah.
Okay. So this is a bounded harmonic function, and we have these are inverses of each other. So LH L is L almost surely, Px almost surely for every x, and H LH is.
Now it's more easy to see that this LH is a shift invariant because the way it's defined, right? Because it's a lim sup of something. So
well, okay, so the exercise that we need to prove, and this is what I messed up last time. Okay, so exercise, what really is hiding inside everything here is that if we have some function H, let's do a real valued function. I mean, it will do everything for the complex valued as well, because I said the lim sup is just on the real and imaginary parts. Okay, if H is a real valued function, what I want, and F is a real valued space-time function, okay, so you have a time coordinate, then lim sup equals to infinity of, so let's call this LH, which we define to be just the lim sup of H of xt, is I measurable, and LF we define to be the lim sup of F of xtt is T measurable. So any limit of a space-time function is a tail measurable function, and any limit of just a space function, a regular function, is a I measurable.
Can we maybe see like the first step of the proof?
So I'm going to prove this. I'm going to do the solution because last time I started proving, messing things up. Okay, solution is very easy. Remember what we said. What does it mean for something to be measurable with respect to I or with respect to T, right? I measurable means it respects the shift, right? So LH is I measurable if and only if, okay, let's assume that these are bounded functions, okay? The reason I want to assume that they're bounded functions is because I want this lim sup to be finite. Otherwise, I have some infinities here, and then I have to say, what does it mean for it to be measurable? Okay, you know what? I'll leave it like this. You can imagine what it means to be measurable on the extended real line. Okay, so including infinity. But, and this is still true. LH is I measurable if and only if LH respects. Last time I tried to do for every this and do the lim sup, it's true you can do it that way, but it's confusing. The easier thing is to say I measurable if and only if LH is equal to LH composed with the shift, right? It respects the shift.
I is where you have some n, right?
Don't you combine respect we said about the measurable partition, and this is like another equivalent.
Yeah, okay, so let's write it differently. If and only if, for every omega, which is equivalent to omega prime, remember what this equivalence means. This means that for some n and k, the n shift of omega is equal to the k shift of omega prime, right? This is the invariant relation. L of omega is equal to L of omega prime. Okay? This is one.
LH.
LH, yeah. Well, we can write L as I. Okay. And L is T measurable if it respects the coarser relation, which is this is easier to be related, right? And this is the double one. Double one means there exists an n such that theta n of omega is equal to theta n of omega prime, the same n for both of them. This is coarser, right? It's easier to be related here than it is to be related. So L respects this relation, it means it's T measurable. L respects this relation.
Why is it easier to be?
Because here,
No, I think this is easier, right? Because you allow any n and k.
sorry, yeah.
What
It's stricter to be
Yes.
T related. It's stricter to be T related, which means anything that's I measurable is T measurable, right? Yeah.
But it works in the other
Okay,
direction.
yeah, go, it reverses. I always, it's easier to be
Yes.
I. There exists n, exists k, specifically if n is equal to k, that's T, right? So it's hard. Okay, good. Okay, so this is what we need to show, okay, for this, right? So we need to show that the limit of a function is I measurable. This is in fact easy because this is equivalent to just being equal to the shift, okay, invariant to the shift, right? And so this is very easy, right? That LH. So LH is equal to LH composed with theta, right? This is easy. Why? Because if you take the limit of h of xt, right? Now you do LH of composed with theta, you get the limit of h of xt plus 1. But that's the same lim sup. So it's the same lim sup because of the subsequence, right? So this is this, which implies that LH respects.
I think we proved that this is being I measurable. So
Yes.
the first.
Yeah, but this relation always shows that you respect this. Okay. That's one thing, and second thing is that so you take omega and omega prime. You know there exists n and k such that they're the theta n of omega is equal to the theta k of omega prime, right? And then you write L of LH of omega is the same as LH of theta n of omega. And LH of omega prime is the same as LH of theta k of omega prime, because you can put as many thetas as you want inside, but then they're equal, so it's the same. Okay, that's how you show this. Okay, so that's done for the H. And for F, why is it T measurable? So if omega, right, we assume we have such a thing, there exists some n such that theta n omega is theta n omega prime, right? So that's right what LF of omega is, right? We need to say that they're equal, okay? This is the lim sup. T goes to infinity of, now what is omega? Omega is a sequence, right? And what does xt do? Xt just gives you the teeth coordinate of the sequence. So this is, as numbers go, this is the lim sup of f of omega at time t, comma t, right? This is what, now this you have to be careful. This is lim sup is not going to be invariant. Why? Because when I shift this guy, the t stays here, right? So there's needs to be some coordination between time and space, which you don't have when you have only space. Space doesn't know about time, doesn't, right? Yeah, I mean,
I believe.
זה בדיבייט, זה בפילוסופיה.
בדיבייט אני אגיד להם.
so, but here you kind of remember what time things, you remember what time things happen, so you only have to be careful, okay? So now, so this lim sup of omega t, t, for large enough t, right? For large enough t, I know that theta n of omega is theta n of omega prime, means for large enough t, t bigger than n, omega t is equal to omega t prime. Okay? If t is bigger than n, omega t is equal to omega prime t, right? So this means that this is the same as the lim sup of omega prime t with t. It didn't change. Okay? Now you see why it's important it's the same n. If it was a different n, then what I would have is that for large enough t, omega t is equal to omega prime t plus something. And then I would have to shift this guy. It would not be the same limit. Not be necessarily the same limit. Okay? So this gives you already an example in a certain sense of a t measurable, non-I measurable object. What happens is when time starts to play an important role.
Yeah, we are going to see that it's actually in a measurable way, it's not
Yeah. Well, wait. That's next. So, but you can think about it. You can think that you can make these like 0 for even t's and just some function for odd t's, right? And then you see that you can't. If you shift the t by an odd number, then you move from something non-trivial to 0, right? So you exactly see those are exactly the games that tell events, non-invariant tail events play. They kind of have some period where they do something, and we'll see that that's exactly the abstraction. That's exactly the abstraction.
So period is the abstraction between harmonicity and
yes, in a certain sense. I will make it precise in the proof. You'll see it come up in the proof. Well, you'll see it in the proof come up what the period means in a sense. Okay, so this is equal to LF of omega prime, and this was true for any omega prime which are equivalent. So we completed the proof. Okay, so I'm sorry for messing this up last time, but this is very easy, right?
שגילוי נאות, זה בין ההוכחות הראשונות שקראתי שהתחלתי את המאסטר, הפרק הזה. אני ככה.
מצוין. תמיד טוב לעשות פעם שנייה. אוקיי. תעשה את זה פעם שלישית ביום חמישי. מביו פוינט אחר לגמרי. זה קצת קשה לי עובד על התרגום. Translating this into the language of ergodic theory is a nightmare. Conditional expectation. Like, this is so much better to view it this way. I'm sorry. This is just, it's not even a preference and it's not taste. It's really just objectively better. This is the way God created the conditional expectation and harmonic functions, not
What is the other thing in conditional expectation in the ergodic theory?
when you have a factor and then you have the conditional expectation.
Yeah.
Okay, so so this is nice. There was one more thing I wanted to say about balancing algebras. What did I want to say about balancing algebras?
We kind of proved now what I showed Blackwell, right? The bijection between I measurable bounded function and bounded harmonic function.
Oh, this Blackwell? Yeah, so it's it's telling you basically that the invariant sigma algebra, L infinity with the invariant sigma algebra is isomorphic to H infinity. Do the product, you can do the algebra again, you can do all that. Yes. This gives you, this is why it's called the Poisson formula. The Poisson transform from an infinity of invariant sigma algebra is exactly what you guys call H infinity. Okay, so another exercise we might want, okay, we will want is, so I didn't define what is a trivial, okay, definition. I think I defined this, but a sigma algebra, sub-sigma algebra,
And for entropy.
P of F is trivial. So trivial, when I teach probability, I just say it's the empty set and the full thing, right? But I'm going to extend this. So it's trivial if, so here we're in the cylinder space, okay? We're in the cylinder, this is the cylinder, right? Okay, so we're in the cylinder G to the N, everything. So if Px of A is either 0 or 1 for every A in the sigma algebra. Okay, so the sigma algebra is trivial in the probability sense, and this is what for which X, you can ask me, which X do you take? All X's. Okay. This is what triviality means. Okay. Now, this is not so trivial to be trivial, okay? Okay. Because to do it for every X, you can have a 0-1 event for some, maybe X, but for maybe a different, you can imagine Markov chains where you'll have some events that are 0-1 in starting from some place, but starting from a different place, they already have probability half, maybe, You can imagine things like that. And in fact, in one of the exercises, we kind of saw a hint of that, where there was a wrong thing and I changed it suddenly without telling you. Right? There was an exercise with a mistake in it. One of the conditions was wrong. So this is really there is something going on here. Okay, saying that for every X the probability is 0 or 1, and this is in a sense what you want by triviality. No matter what starting point or what viewpoint I take, I still have 0-1 event. Okay, and I didn't say it could change from 0 to 1 maybe. Didn't say. Now. Exercise. The invariant sigma algebra is special. I is trivial if and only if for every bounded I measurable L, random variable L, okay? There exists a constant okay, such that for every X in G, now the quantifiers are very important here. Probability X of L equals C is 1. If I was to say this for a general sigma algebra, this is trivial, this is easy, this is very easy. But if I was to say this with the X before the C, if every one of your events has probability 0 or 1, then all the bounded random variables, the G measurable random variables will be constant, but they will be different constants for different measures. Might be, okay? And in a sense, you can think of it, an event can have probability 0 in one probability measure, and probability 1 in a different probability measure.
Do event on the first, like on the 0 coordinate, and then.
But I is special such that it does not change. The constant remains the same for all the starting measures. Why? You're using two things here. You're using the invariance, shift invariance, and you're using what else?
Reducibility.
Yes, you can get to any point in the Markov chain. Okay, this is the important part. Right? Because if I know I'm constant starting from this point, and I'm invariant, well, I'll just walk to that point and then start from there using the Markov property. But I was invariant, so it has to be the same constant. Okay, so I basically told you the proof. The easiest way to prove this, in my opinion, and I think this is the easiest way to prove this, you might have a shortcut, is to just do it first for events, which means for indicators, for L is an indicator of an event in I, right? And if you know it for indicators, then you know it for finite linear combinations of indicators, then you know it for limits of finite linear combinations, so non-negative I-measurable random variables. You know it for non-negative, you know it for general I-measurable random variables. Okay? If you know it for general real valued measurable, then you know it for complex value. Okay? By taking positive, negative parts, and right. So if the positive and negative part have to be constant, then they're random, right? And if the real part and imaginary part have to be constant, then they're random. Okay? So at the end of the day, you can get anything complex, but all you have to do is just for indicators. Okay? Once you do it for indicators, the rest is the usual measure theoretic way of going up the ladder. Indicator. There's in fact a lemma. I never teach this lemma because I feel it's more confusing. There's this lemma, what's it called when you do? There's a lemma that kind of says anything you can prove for indicators, you can also lift to general complex valued random variables by going up this ladder.
Victor calls it details exercise.
No, but there's like a lemma, I forgot what it's called, like you have you define some abstract property, like, because, okay, anything you can prove, what do you mean? So you have like, I have a family of random variables that satisfies the indicators are there and they are closed up to a linear combination, right? And then, so then you show that the property you're trying to prove, for example, this property, that for every x, it's a constant. You show that the indicators are there, you show that it's closed under finite linear combinations and limits and whatever. And then you get it from the lemma, I get this, right?
If we would try to use the Poisson formula, what would we get? We get an harmonic function that like, could we use it or?
Maybe. If you give me an alternative proof, I'll be happy. I did the first thing that came into mind. If you know a bit of measure theory, usually that's the first thing that comes. First, check for indicators, okay? Then, you know, if it's good for indicators, then you think, okay, well, how can I go on, right? I mean, if it's true, it has to be true for indicators, right? Okay, so that's what I wanted to say about invariant and tail. So let's go back to entropy. Go back to entropy. Entropy and the tail. Okay. So you remember that we proved that the random walk entropy remember that we proved that the random walk, I denoted it, I think, like this, right? Or without maybe random walk on the bottom, just H. Now I'm starting to get confused because I'm preparing the Thursday talk and there it's denoted a little on. Right, so this is the limit. This was defined to be the limit as n goes to infinity of the Gibbs-Shannon entropy of the time n, right? But we also proved that this is the limit of the non-increasing sequence h of xn minus h of xn minus 1, right? We proved that this sequence is non-increasing and therefore it must converge to the same limit as this sequence just by telescope. Okay? And now I want to develop this guy a little bit and see what it says. I think we already did this, but let's develop it a bit. How can I write the entropy of xn minus 1 in a group? Now it's important that I'm in a group. Well, the distribution of xn minus 1 is exactly the same in terms of probabilities as the distribution of xn conditioned on x1. Right? We said, remember we did the trick when we multiply on the left by x1 minus 1 and we get, what?
Markov.
Yes, it's a Markov property basically, but it also uses the fact that I can multiply, so I can shift everything to the perspective of the original, right? So I mean, if xn minus 1, you can take a copy of it. This is equal in law, has the same distribution as x1 to the minus 1 of xn. These two are random walks on the group at time n minus 1. N minus 1 steps. Okay? They're not the same random variable, of course. Not equal, but they're equal, they have the same distribution. So their entropy is the same. Okay? They both have the law of the n-1 convolution power of u. Okay? So this can be written as the entropy of xn minus the conditional entropy of xn conditioned on x1. Right? We did this trick in the past. Okay, when we did the Kaymanovich-Vershik entropy criterion. And this is equal to, remember what this is. This is the information, right? This is symmetric in xn and x1. Right? Because what is this? This is the pair minus x1, right? So you get h of xn plus h of x1 minus the entropy of the pair, but everything is symmetric and you can exchange order. This is also equal to h of x1 minus h of x1 conditioned on xn. This is the magical symmetry of information, which you cannot see when you look at entropy, but you know it is true. Right? Because these two are equal to I x1 xn, which is symmetric. Okay? And now, what happens here, remember we said that this, if I know the future, if I condition on time n, this is the Markov property, then I can add as much as I want here, right? It doesn't give me more information. Same, right? So this is equal to h of x1 minus h of x1 conditioned on xn plus 1. And in fact, I can go off all the way by taking limits. We said that these converge to the natural thing, right? I can even put the sigma n. Remember, sigma n was the tail, right? The one giving the tail. But then I can take n to infinity, right? Because I want the limit here. So what is this limit? The limit, n goes to infinity, of h of x1 minus h of x1 conditioned on sigma n.
H of x1 minus h.
Right? And this is why I was very important for me to define conditional entropy with sigma algebras, not just with random variables, because you see, we really need it in this analysis. And we also wanted the martingale and backward martingale convergence to prove this one. These are the decreasing ones, so this converges. But we proved already that this converges to the intersection of all of these. But the intersection of all of these is exactly the tail. So you get this. Another formula that I will prove again on Thursday.
T is what we denote by sigma, right? In the homework. Just the intersection of sigma n.
T is the tail. So the tail was defined to be the intersection of n of sigma n. So definition of the tail sigma algebra. We showed that it's equivalent to this respecting
the continuity of entropy, right? Or something like that.
We use the fact that if you have a non-decreasing or non-increasing sequence of sigma algebras, then you know what the conditional entropy converges. Here, it's a non-increasing sequence of sigma algebras. So the limit of this thing converges to the intersection. Conditioning on the intersection. Here, it was an increasing sequence, non-decreasing sequence of sigma algebras. So the limit converges to the sigma algebra generated by the union, which is exactly the sigma ends.
For proving that, I don't think we use the continuity, right? Or we use
For what?
for what you pointed out, that you can take x1, xn plus 1, and it would be sigma n.
For this, yeah, you use continuity because you first show that this is xn up to xn plus m for any m.
Yeah.
And then when you take m to infinity, you get here sigma n. When you start putting infinitely many guys here, you have to be careful. You get the sigma algebra generated by this increases as a limit the sigma algebra generated by the union of all of these finite ones, but that is exactly the sigma algebra generated by xn to xn. It's very intuitive in the notation, but that's why we use this notation. You have to, at some point, you have to prove it works. Okay? So we got a formula for the random walk entropy. Look, there's no limits on both sides. Okay? So, very important formula. I think this first appears in Kaymanovich-Vershik, if I'm not sure. So the random walk entropy was already studied by Aviz, but I think this appears in Kaymanovich-Vershik. So theorem, what we have now is that the random walk entropy of G mu is equal to just the information the tail gives us on the first step, right? There's how much entropy I need to make one step. That's just the entropy of the measure, right? U. Then there's how much information I need for the first step if I know what happens at infinity in a certain sense, if I know the tail, all the information in the tail. The difference between that is how much more entropy do I need to decide the first step without knowing the tail, right? That's the difference. So this is the information the tail gives you, right? It's the information that you still need if you know the tail. Knowing the tail takes off some information and you're left with what you had. Okay, so this is so it's how much you remember, like how much does the conditioning at infinity affect your first step in a certain sense. Okay? So entropy is related to the tail sigma algebra, not the invariant sigma.
If I would tell you what happened in the end, you would maybe get more information to know what would happen in the first step.
Yeah. So for example, in the free group, the tail sigma algebra will be kind of which ray did you end up going in. In the free group, it's tail is kind of given by a collection of subtrees further and further down that you ended up in. So you're kind of it gives you an end. And if you condition on going into a certain end, then it changes the distribution. Conditioned on going to a certain end, the distribution of the first step changes. You have more probability to go in that direction than in the other direction. You just can't go in the other direction because you could go and come back, right? But the farther away you go from this thing, kind of exponentially decreases. So it changes the distribution, but it does not become zero. It does not become zero entropy, this new distribution. But for example, if you condition, if this happens to be true, if you condition on the information at infinity in ZD, or even in Z, then it doesn't give you any information. So the entropy of the first step is the same as the entropy of the. So conditioning on what happens in infinity doesn't change your distribution. You still don't know if to go right, left, up, down. You're still ambiguous about, what actually is happening. It doesn't change the distribution. In a certain sense, if I tell you exactly where you are at a very, very, very large time, and I want the conditional distribution of the first step conditioned on that of course is different, but the larger this large time is, the less it changes, the closer it comes back to the distributed uniform on the generators. And in the free group, it's completely not true. If I tell you you're down there, then you have very little chance to go deep into a different place, right? So it's much harder to do. That's about entropy. But we want to relate to bounded harmonic functions. So we already get, for example, theorem. Zero entropy is equivalent to
Trivial.
every bounded parabolic function is constant. That's what it says.
And what did we show already? We showed something about zero. We showed when the entropy is zero, then.
Yeah. So when the entropy is zero, then
Or the bounded harmonic function.
Yeah, then all the bounded harmonic functions. But we did that using the Coulomb inequality.
Yeah.
Well, that's the easy direction. Okay. Okay. Now I could have extended this. I could have extended this analysis. So exercise. What happens if you did x1, xk, then took off the conditioning? T steps of that.
Yeah, up to step K.
Yeah. Step K. What happens then?
K,
So-
A,
You need to think about it for a second. Okay? But I mean, the first one is easy. This is just K of x1. K times x1, right? Because you keep taking off one, right? But what happens if you do this, you get K times the random walk entropy. Now, so now this already tells you something about when what happens when the random entropy is 0. So this tells you that the random entropy, so corollary, if you do that exercise, okay, corollary, but it's the exercise is the same as this analysis. And it's just the same, you just have to be careful with the case, right? You transfer back everything to everything finite, right? Take some large n and you replace t with some large n because you can, right, in the limit. And then you ask what is the difference when you have x1, xk, and xn, and we already did that computation, and you get something, and then you take the limit as n goes to infinity, and you get exactly this. So you'll just get a telescopic sum of k different guys like this. You'll get a sum of k different guys like this, but a different things. But when n goes to infinity, you get them all converging to. Okay, so the corollary is that h is equal to 0 if and only if what? Remember, what did we say about conditional entropy being 0? Conditional entropy being 0 means the random variable here is independent. Sorry, information being 0. Information of a sigma algebra being 0 means this is independent of this sigma algebra. Okay, so if and only if, let me write it this way, ft is independent of t for every t.
Then because of the 0, 1 is being trivial. Because
exactly, and this is the exercise. Kolmogorov 0-1 law is exactly telling you. Kolmogorov 0-1 law is exactly the theorem that says that when you have this situation in the cylinder sigma algebra, when you have this situation, the tail is invariant to the first t coordinates for every t, it is independent of the first t. Then the tail sigma algebra is trivial. So theorem, the exercise to prove it. I stated it and I gave it as an exercise. I didn't. Kolmogorov 0-1 law. If ft is independent of t for every t, then t is trivial. Trivial in what sense? In the sense that every event in t has 0-1 probability for every x, right? Because you can do this specific, you can do it separately for every starting measure. I mean, the independence now, this is independent of t. Okay, yeah, independence needs a measure, but we can do this for any starting measure. Okay, yeah, so right here, if and only if f is independent of t for every t and for every px. Because that determines independence. I mean, probabilities determine independence. Here you can just prove that if ft is independent of t for some px, then t is trivial for that px, and you just do it for it. Kolmogorov 0-1 law is really about one measure, not about a family of measures. Okay, so we get that the triviality of the tail sigma algebra is completely equivalent to 0 entropy. Equivalent, not just one direction. Okay, but we wanted to say something about bounded harmonic functions, which has to do with the invariant sigma algebra, and not about tail sigma algebra. And so this next theorem that we want to prove is that triviality of one implies triviality of the other. Now, of course, triviality of the tail sigma algebra implies triviality of the invariant sigma algebra because every invariant event is a tail event, right? So we already have, and this is the third or fourth time we're proving this, right? We already have that this equals 0 implies that I is trivial in the sense that I said before, right? Because it implies T is trivial. But the other direction we don't know because I being trivial does not necessarily a priori imply T is trivial. And we will show this. So what we want to show in the next hour is that I being trivial implies that T is trivial. And we'll show this. We'll use, my trick is to use parabolic and harmonic functions to relate them. There are other ways to relate them. What?
Something you promised us like a month ago.
Yeah,
That will prove.
maybe.
We're excited about
But
P.
this works in a group. Here we'll start using the groups, right?
Don't you show it in the book in more general that the T measurable is just null extension of the I measurable?
That's what I'm going to show.
So this is a okay. Would be a corollary of that.
Yeah. But why do I want to show this?
Yeah.
I want to say, okay, I want to go the other direction. I want to say if all bounded harmonic functions are constant, which is completely equivalent to I being trivial, because we said bounded I measurable random variables is exactly the correspondence with bounded harmonic functions. So if they're all constant, then all the I measure ones are constant, meaning I is trivial. Then I want to prove that entropy is zero, because I want to prove the other direction. Okay? And then I'll have a fifth theorem that entropy is zero if and only if I is trivial. But this is going to be true random walk on a group and not necessarily on a general graph. Okay? Well, we don't even know that entropy converges on the general graph. But I'm just saying, you have to be careful. Entropy has to do with tail, parabolic functions, and invariant sigma algebras have to do with bounded harmonic functions or harmonic functions in general. These are different objects in the widest possible view. Okay, let's take a break and then we'll begin. Okay, so what? So the goal is clear now. What we want to prove is the triviality of I implies the triviality of T. The other direction is easy. And to show this, we will prove that every event so every invariant event is a tail event, right? But we'll show that every tail event has a cousin which is an invariant event, and that invariant event, the difference between them has measure 0 in all the px's, okay, or any x. So basically, you cannot get a new non-trivial thing from tail if you know that all the invariants are trivial. Yeah, I mean, if you know that all the invariants are trivial, then you can't get any, like, we'll just get more, you might get different events, but they will still all have a measure 0 or 1, okay? So this is how we're going to show it, and we're going to show it through harmonic and parabolic functions. Okay, so the first thing I want you to notice is that, let's do, now I'm going to do general probability measures, not necessarily symmetric, not necessarily adapted, just general probability measures on the. Suppose I have the situation where mu is p times delta 1, p is some number inside 0, 1, p times delta 1 plus 1 minus p times nu. So nu is some measure, okay, and mu is a different measure. What is mu? Mu is the measure that says, you choose a random element, with probability, just choose the identity element. And with probability 1 minus p, choose an element according to the measure nu, right? Now, what happens if I do the mu random walk? Right? What happens if I do the mu random walk? At every step, with probability p, I don't do anything. I just stand in place because I multiply by the
lazy.
Exactly, it's a lazy random walk. So mu is the lazy version of nu, right? Now, what does that mean? What is a lazy version of nu with the same p? It means that you can sample mu at time t, right? By sampling, first of all, how many actual steps did you do? How many did you do? Well, you have to decide at every stage, did I move or not? I stay put with probability p, and I move with probability 1 minus p. This is a binomial random variable, right? How many actual moves did I do? I did binomial 1 minus p. Binomial t 1 minus p, right? And if you sample first that binomial, and then independently sample nu, right, at that time, binomial gives you a time, okay? Then you get exactly the same distribution as mu. So I'll write this down as an exercise, but this is an easy exercise. If xt is a nu random walk, and B is binomial T 1 minus P independent of xt. Okay, so if you write, you have an easier proof of this?
It's more algebraic, but you do
Convolution,
t times t convolutions of mu with itself,
You get a binomial.
and convoluting with delta 1
Yeah.
doesn't do anything.
Because it's, well, it's, yeah, but it's also commutative, so you get the binomial coefficients, that's where the binomial comes from.
Yeah.
But for me, it's easier to think about it as a random process, a dynamical process. You'll see in a minute why this random viewpoint is useful, okay? So if xt is a new random walk and b is an independent binomial random variable of these parameters, okay, so I'm thinking of b as how many times did I actually walk in mu, then u to the t, we should write it this way. Okay, so then the probability that xb, so b is an integer, a non-negative integer, so I can write xb, right? It makes sense. What is xb? It's what is new at this time. This time is just stayed put a few times, right? Exactly the correct amount of times. So the probability that xb is equal to x is exactly the same as mu convolution t at x. Okay? So if you want to get the mu t distribution, you sample the new distribution and you look at it at a random binomial time. Okay? And I think that the proof is easy. You just write it down, but, or by induction, or it's not so hard. But now I want to use this. Okay, so I want to give you another exercise, and the other exercise, which might be a little more difficult if you're not used to probability, but it's worthwhile thinking about. There exists a coupling of B, which has binomial T1 minus P, and B prime, which has binomial P plus 1 minus P. I can go one more step in the second binomial, okay? And I want to couple them. So I want to put them in the same space. The marginal distributions are correct. They both have the same, the correct distribution, okay? But I can put them in the same space so that the probability that they're not equal is of course not independent. It's a coupling, meaning they have a connection between them.
Wait, we didn't say that xt has a law of nu.
Yes, xt is a new random walk.
Sorry.
So the probability they're not equal is less than some constant divided by square root t. And I can even write down exactly who this constant is if you really want to. Okay. There are a few methods to prove this. One way to prove this, think of binomials as kind of random walks. If you recenter them, if you recenter the binomial as a random, if you recenter it, okay? So if you take this and subtract, so you can, so instead of moving right every time, right? So you want to move sometimes right and sometimes left. Okay, so you recenter it so that it moves right and left with probability half. So that's shifting this by some constant. Okay, and shifting this by some constant, and they're both random walks. And the probability that two random walks, you can couple them together so that even if one starts, so that you can couple them together so that if one starts one above the other, then they reach the same point eventually, because the difference between two random walks, okay, is just, so the difference between two independent, or sorry, you can couple two independent random walks. You can couple two random walks, not independent. You can couple two random walks so that they either move apart two or move one, right? And you make them lazy, or if you start at distance two or something like that, you can make them exactly, you can couple them so that one stays and the other moves, or this one stays and the other moves. and then the distance between them always grows or shrinks, and that exactly looks like a random walk. And so the difference between, yes, what am I saying? Well, anyway, you can think of the difference between these two guys as as a coupling between two lazy random walks, and use that to show that the difference between two lazy random walks is a symmetric lazy random walk, and a symmetric lazy random walk will hit zero eventually, and you can estimate the probability of how long it takes it to hit zero when it starts from one, right? So the one comes from the difference in one step here, right? And then you can get that. But there are other ways of doing this. You can compute the total variation distance between these two measures. It's also easy, because here you know the complete density, you know everything, right? So just complete the total variation distance between these two measures, and you get that it's specific constant, bounded by specific constant divided by square root. Okay? So this is just a probability exercise. You can couple to, think of it, I mean, the easiest way to think about it is, by the way, this C depends on P. So you have to be careful, but maybe it doesn't depend on P. Well, it could, I don't really care, okay? So make it easier if I make it depend on P. But you can think about it this way. I toss many, many coins, okay? Toss a lot of coins, right? And so I tossed 1,000,000 coins and 1,000,001 coins with the same P. And I just want the probability that I don't, you know, I just want to say that they have pretty good chance of seeing this if I couple them in the right way. And there's a pretty good chance that I've seen the same number of heads, right? And the way I do it is that I toss, you know, for one and the other, and I have enough freedom to like say, okay, this is what one came out. Somehow you know, it's the same number as the other one came out by just changing a little bit the measure and evening things out. So it makes sense that as t gets bigger, these things will become closer. Okay. Good. So this is something that I'm going to use. What do we want to do? So the first lemma that we need, lemma. Again, in the context, there mu is p delta 1 plus 1 minus p nu. Then any bounded mu parabolic is actually mu harmonic. The walk is lazy, then a bounded mu parabolic function is actually a mu harmonic function. It doesn't depend on the time coordinate, right? That's what.
Any u parabolic is what?
Bounded mu parabolic is a mu harmonic. Proof. Let's prove this level.
Not assume anything special about it.
What?
About new. Don't assume anything.
No, just probability. Let Fn, right, sequence, we're going to think of this as new parabolic, right? Be a bounded new parabolic. Okay.
We are now showing that any mu parabolic is mu harmonic.
Bounded mu parabolic is mu harmonic, meaning if I take this sequence, then actually Fn is equal to F0 for all n.
You said it's a lemma, but doesn't that show us that they're
No, because I assume that mu has a special thing with a p non-zero here.
for that p?
For lazy random walks, this works. Anything that has some p to stay put, yes.
And then they are the same. As
Then it shows that I and t are the same, but we want to get it for any random walk. This shows that actually I and t are not different. Really,
based on the Boston formula.
yes. But but this is only in the lazy case. In the lazy case, you get rid, this is what I talked about, periods. There are no periods, so the time here in the parabolic doesn't help you get anything new. Let be a bounded mu parabolic function. So we want to show that Fn is, and so you fix n, and I want to show Fn is equal to F0. Right? If I show this, then I'm done. Right? Okay? So how do we show that Fn is equal to F0? We use the martingale, right? Let's see, Fn of x. I claim that this is equal to the expectation starting at x of f of what? Martingale is you have to take t steps of a random walk and t plus n here, right? Because you need to get to the Fn. Okay. Now, you have to be careful. Okay. And the same is true if I would take here n plus 1. Okay? Now, let y be a new random walk, and let b be binomial t 1 minus p, and b prime be binomial t 1 minus p, t plus 1 1 minus p, such that coupled such that they're equal with very high probability. Okay? In fact, I don't care about the square root of t. All I care about is that it goes to 0. Okay? Now, we take t, and we know that y, now what do I want? I have to be careful. Which one do I want? I want to go t steps in the n plus 1 case. Yeah, okay. So we know, okay, so yb has the same law as x t, and yb prime has the same law as xt plus 1. Right? They have the same distribution, or if you want, this is mu to the t is the distribution of this, and that's the exercise we had before. Right? And so this means that I can write the following. I want fn of x minus fn plus 1 of x. I'm going to show that these are equal. That proves that all the fn's are the same function, right? If I show it for every x. This is exactly equal to what? Well, I can do this, the expectation, starting from x, and f, now I have to take this guy, right? And so I'm going back in between the space-time and the sequence thing, but you understand what I'm doing. Now, you see, this one is n. So here I'm going to have a t plus n, right? So let me do this one. Let me do this one at time t plus 1 plus n, right? What? And then I need to put here an xt plus 1. But xt plus 1 has the same distribution as yb prime, right? So I could do the yb prime. Okay? Because this has the same law as xt plus 1. I did xt plus 1, t plus, right? I just plug it into this expectation. It's the same, put everything in the same space. Okay? Then minus the second one. This is a different expectation. I can do whatever I want in there, right?
Fn of x is
T is
defined by
fixed.
t.
T is fixed. I fixed t.
How can you take t plus 1 and then say this is the same as Fn of x?
The expectation, if you fix a t and you have an n, and you look at the expectation of f at time xt plus 1, t plus 1 plus n, this is a martingale. And so it's equal to itself at time 0, at time 0, you have f of x0, which is x and n. The time now is t plus 1. I took time t plus 1, t
No,
plus 1.
I'm just saying that f of n is defined at time t. So I'm going to take time t plus 1 and say this is equal to fn.
This is a martingale. So this is also equal to
Because of the,
going with t, any t. It's true for any t.
yes, okay.
I fix a t, but now I do it with t and with t plus 1.
Okay.
This one is with t plus 1. And this one I do with t. When I do the one with t, then I want xt. So what has the distribution of xt? That's yb. And here I have t plus, but this was n plus 1. Okay, let me stress that this here, the t plus 1 was going at time, and here the n plus 1 was coming from this n plus 1. Okay, maybe I colored it. It'll be clear. So this t plus 1 goes with this t plus 1. And this n plus 1 goes with this n plus 1. This n goes with this n. Okay? טוב? לא ברור? Okay? Okay, but now since I've translated everything to these b's, I can put everything in the same space because now b and b prime were coupled to live in the same space, so I can put them in the same space. So what do I get? I get that this is ex of f of if I put absolute values, I can, right? So the difference in absolute values, I can just bound by bringing the absolute values inside, right? With the absolute value of f of y b prime t plus 1 plus n, but t plus 1 plus, right? You know that t plus 1 plus n is the same as t plus n plus 1, right? It's the same thing, right? So t plus n plus 1. But you see, they came from different places. That's the trick. They came from different places. Plus 1s. Okay? And this is less than or equal to, well, what happens? If b is equal to b prime, I have the exact same group element here. Right? So this is 0 on the event that b is equal to b prime. The only chance for this to be non-zero is that b is not equal to b prime. Now, I use the fact that f is a bounded parabolic function, right? This is not true in general. This is true for bounded parabolic function. Well, you can generalize it if you have some bounds on how f grows. But anyway, it's a bounded parabolic function, so I can just bound everything by the infinity norm, twice the infinity norm, because it's this minus this, so I plus. And I have an indicator, right? I can multiply this whole thing by an indicator that b is not equal to b prime, but then inside the expectation, I only have this goes to 0. This goes to 0.
Okay, wait. No, but now it goes to 0 in what sense? Because like what we fixed it, then we get
Now
b.
you said that this is true for everything.
Let me write both sides of the equation that we got. We got the following thing. For every n, or every t, okay? Fn, and for every x. Fn x minus Fn plus 1x, this was the left-hand side, is less than or equal to 2 times infinity norm of f times some constant divided by square root t. T is only on the right side, n is only on the left side.
Okay, so the lemma that was written there, that like when you fix the p, you can do it for any t to find that constant. Because what happened? We okay for any n and for
I
any
fixed
t,
p. P is fixed.
is big.
This c can depend on p, no problem.
Like what we do something like we have a lot of couplings. We for t equal
P is fixed for the whole lemma,
no
because
not
p
p
is
not p but b for
p.
yeah.
This one is fixed for the whole lemma.
Yeah, but those b's are for every t you create new b's, right?
Yeah, but this inequality, I fix a t, I prove this inequality. Fix n, fix t, fix x, get this inequality. But it holds for every one of them. A quantitative inequality. It's not just a. Okay. Yeah, it's a different coupling for different binomials. Yes, of course.
So every step for every t, we have new coupling, but then we get this.
Like you can do, if you took the random walk approach, all you needed was that some symmetric random walk reached zero, and the probability not to reach zero by time t is decaying like 1 over square root t. That's what you want. Okay, so in fact, you could have a coupling that goes for all t once and for all, but I don't need it for this proof. I just need one coupling for fixed t to get an inequality. Okay. Now, of course, I take t to infinity on this side. I get 0. So what do I get? I get that fn of x is equal to fn plus 1 of x for every n for every x. But this shows that f does not depend on the time coordinate. This shows that f is a harmonic function. Right? So this is the end of the proof. יש בעיה נראה לי, אני לא יודע אם אתם רוצים להתערבות או מה.
זה בסדר, המודול הוא התרגיל. עדיין היסטורי וזה.
הקפלינג כאילו?
Total variation distance, אפשר פשוט לחשב את זה.
לא דיברנו על קפלינג פה, נכון?
לא דיברנו ממש.
זה כמו ג'וינינג. שבג'וינינג אומרים זה כמו קפלינג. זה מעגלי.
אם אתם רוצים, אנחנו נוכל לדבר על זה. Okay, let new, yeah. Okay, so now we want to prove that the actual gain. Okay? Okay, so now we prove the actual theorem. So mu is adapted. By the way, I'm showing you something that's true for, I didn't assume symmetry, I didn't assume anything. Now I'm assuming adapted. Okay? This would be important if I wanted to talk about Choquet-Denis theorems and stuff like that. So maybe for us it's not so important, but anyway. mu is adapted on G.
You also cared about those kind of stuff.
Yeah, well, I will maybe talk about it tomorrow. mu is adapted on G. And what did I want? And for any tail event, okay, there exists an invariant event B such that for all x in G, the probability of the symmetric difference between A and B, okay, is 0. Specifically, right, if I is trivial, T is trivial, right? This immediately implies. A and B do not depend on the X. I mean, you have A, choice of B does not depend on X. Okay, so let's prove this. Let's prove this. You'll see where adapted comes up. Adapted is used to create a lazy version. Right? First, choose once and for all. So choose once and for all K such that, so xt is the mu random. Okay? Choose once and for all K such that the probability that xt is 1, so probability starting from 1, that, sorry, xk is 1, and I want to choose K at least 1. So K has to be bigger than 0, not 0. Okay? Probability that I came back to 1 at some point is positive. Why can I choose this K? Again, adapted, right? You first take a step, you have to move away from 1 at some point, right? So there's positive probability to move away from 1 because you're adapted, right? And then from that point, whatever it is, there has to be a path coming back to 1, right? So there has to be a positive probability of coming back to 1 in some time in the future. So I can find such a K.
If mu is already been lazy, then K is 1.
Yeah, so you could take K1 if you is lazy, you could, if you is not lazy, but it's symmetric, you can take K to be 2, go back and forth. Right? Those are basically, you know, it's for symmetric probability measures, everything becomes nice and easy. Okay, but you see, this is the periodicity issue. Exactly. Can I come back to 1 or not? Or when do I come back to 1? When is the first time I come back? You could take the minimal K, right? So how long does it take? What are the cycles, the minimal cycles? This is periodicity. The minimal cycle is of length, I don't know, right? Is of even length, and you have a period. Good. And now define nu. What I want nu is going to be the probability measure, which is so let's call this number P. Call this number P. And nu is going to be the probability measure, which is conditioned, which is kind of conditioned not to be back at 1. Okay. So how do I condition? Well, I take the measure where you are at time K, and I'm writing it in the style of be more ergodic theory or measure theory style, right? So you want to be you take your kth step distribution, you remove P times delta 1, so you take off the mass that you give to being at 1, which is P, right? And then you divide by 1 minus P so that you get mass 1 again. This is just conditioning. This is a distribution of xk, conditioned xk not equal to 1. And you can do this, everything is well defined, okay? Good. What does this tell you? This tells you that mu to the k is a lazy version of nu. Okay? Now, nu is not necessarily adapted. It's important for me that I didn't need to assume nu was adapted before. Okay? So you see that mu, okay, is P delta 1, it's 1 minus P nu. Nu is some probability measure. Okay? What am I thinking of? I'm thinking of just mu, since it has a positive probability of being back at 1, then if I look at every k steps, I can think of that as a lazy version because it has a positive probability of not doing anything. And with the remaining probability, it does some nu, some weird thing. That's exactly what nu is. So this is what I'm thinking of. Okay? Good. So what do we know about mu? Right? So now,
Take
we take some tail event, and we take, right, so we want to fix a tail event and find the corresponding invariant event, right? So, and that will go through the corresponding bounded parabolic and harmonic functions. So let A be a tail event, and there exists Fn, which is a mu parabolic function, right? Which corresponds to the indicator of A, right? So that A is the limit of this thing. So, or if this function is the yeah, okay. So we can write this way. So there exists a mu parabolic function such that the probability under X that Fn xn converges as n goes to infinity to the indicator of A is 1. And this is for every X. I mean, it's enough to say for one X, for each X separately, and then, I mean, there are only countably many of them, so it happens in probability 1 for every X. Right? This is a bounded tail measurable thing, right? So we can take the corresponding bounded parabolic function, and we know that the lim sup of this function is going to be something that is equal to this up to measure 0, and in fact, bounded parabolic function gives you a martingale, so this thing converges almost surely.
Is it the convergence in measure or something like that?
It's almost sure converges. Converges.
It's just I'm sure. Okay. Yeah. Sorry.
You can say that there is a measure, there's a indicator which is equal to the same to this indicator up to measure 0, meaning there's an event which is the same as A up to measure 0, A prime, such that with a parabolic function that whose lim sup is exactly the indicator of A prime. But we know that parabolic functions also converge almost surely, so their almost sure limit must be this indicator. Okay, that's all I want. Good. Now, let's consider following sequence. We don't want to look at every one step. I want to look at the every k steps. And in fact, I don't care about looking every k steps from 0, but rather I look at k plus L. Now I run over all the ends. Okay. Now what does this look like? What is this thing? So we consider this sequence. L is some fixed, there. L is some fixed number between strictly less than k. Okay? And k is my fixed k from the beginning. K was special. Okay? Now what is this thing?
UK parabolic.
This is mu k parabolic, right? I apply p to the k p mu, right? My transition matrix, k times to f k n plus L. What do I get? Or let's say k n plus 1 plus L, right? Each time I apply it, I have to take off 1 because f was mu parabolic, right? So I get f k n plus 1 plus L minus k. So it exactly takes away this one. Okay? So you see, as a sequence in n, this thing is mu k parabolic.
It's saying that the p to the k of mu is like p to the mu to the k.
It's the same.
Yeah.
No, but here I'm applying the operator. If you want, I can do it with the convolution. It's the same thing as doing the convolution. Remind myself which side I need to do convolution on. Okay? Mu to the k parabolic. All I need is and it's bounded, of course. I mean, the bound is the same, right? The bound is the L infinity bound. So it's mu to the k bounded parabolic, right? And mu is lazy. Mu k is lazy. What do we get? We get that for every L between 0 and less than k, and for every n, f k n plus L is equal to the one at 0, which is fl. This is from the lemma, right? The lemma that I did before, the lazy version. You see why you need the lazy version? The lazy version takes care. What I did is a periodic decomposition. I decomposed it into periods. See what the periods are. The periods are the k periods, right?
The f L, right?
Right.
No problem.
And specifically, since this is true, this implies that FL is mu to the k harmonic for every L. Okay? Right? Because when you apply mu to the k to a version of it, it goes down, but they were all the same. So it's mu to the k harmonic, right? This is what it is. Okay? I decomposed it into k different periods, 0, 1, 2, up to k minus 1. And now I have to take care of the periods. How do I get a mu harmonic function from these different k mu k harmonic functions? I have k different functions. Each one is mu to the k harmonic. I want to get a mu harmonic function for this. Any ideas how to do it?
Range.
Sum or an average, right? Just right? So you're fine. Do this one, but you can even just take the sum. I don't know why in the notes I wrote it this way. You sum these guys and you put here an FL. Okay? Now, I claim that G is mu harmonic. Let's see. What is P mu of G? What is P mu of G? Okay, so what does P mu do? 1 over K. Sum. Now I'm going to do it this way. Okay, I'm going to do it this way. I don't want the 0. I don't like acting on the 0 function with the P because I was assuming parabolic, right? I don't have information about the parabolic at 0, right? So I'm going to,
From 1 to 10.
but L I can add K, right? Because it doesn't matter, right? Because I know this. So this is going to be L goes from 0 to k minus 1, P mu acting on F L plus K. I can do that. I'm allowed to do add K to each one of them, right? Because of this. Okay, no problem. What is this? This one goes down by 1. F L plus K minus 1. Right? Now let's see, what is this doing? This is L is going from 0 to K minus 1. So this thing is going from K minus 1 up to twice K minus 1. Right? So I could exchange this for sum 1 over K. Sum L goes from K minus 1 to 2 times K minus 2 FL. Okay? But now, I'm confused, 1 second. So now what do I get here?
I can suggest that we can, in the sum, just do from L from 1 to K, not from 0 to K minus 1, G. Then we just get, it's the same sum, but not all these K's and blah.
Yeah, that is true. And we make it easier to, I mean, it's the same computation as here.
Yeah, but it just is.
Okay. Yeah, so what you need to notice here, instead of doing L plus K here, that's right. You should notice that this is the same as going from
Does it
1
really matter that
to K.
they're the same, right?
The only thing that you
It's
need.
the same, we just exchange the order of summation. Because F0 is Fk.
Yes.
Yeah.
That's the only thing I do. And then here exactly, good. So I have from 1 to K, FL, and then this becomes just 1 over K, sum L goes from, because I take one off, right? So it becomes L goes from 0 to K minus 1, FL, but this was the same as G because we already said that there. Okay, so we found that G, and G of course is bounded. I probably took the average because I was thinking of keep the same norm, keep the same bound, right? But even if you just take the sum, you just bound it by K times the norm.
G, new harmonic or new K harmonic?
You. So this was just applying one P.
Okay.
It shifts every one, and there's a period, so you go back to the beginning,
Yeah.
right? So PG equals G implies G is mu harmonic. This was not P of mu K, but rather P of mu. So G is mu harmonic and bounded, right? So this means that G xt converges as t goes to infinity, px almost surely, to some random variable, which we can call L. And what is L? L is invariant. Yes, Martingale convergence. But we said if we have a bounded mu harmonic function, we know it converges almost surely, and we know that the limb sup is exactly a. Okay. Now let's see what is L. What is L? Right? L. I mean, L has to be the indicator, right? Because G is just an average of these guys, okay? And they all converge, subsequences. Okay? So let's see what happens.
It's an indicator because we want to say it's a 0-1 function or something like that. Like
Yeah.
how would we know it's an indicator?
Yeah. So this is what we're going to show. We're going to show it's an indicator. Okay? So we need to look at what limits are possible for this G. That's what we need to do. We want to look at what are the possible limits for this G. Yeah. So all I need to do is just look at one of these guys. So let's look at G of x k in. Okay, let's look at what this converges to. Let's take it with a period of k. Okay. So I wanna ask, what does this converge to? Okay, now what is this? This is equal to 1 over k sum L goes from 0 to k minus 1 f L of x, FL of x at kn, right?
We had KN, right, to L.
Yeah, I can add kn to L, but I want
It approaches also L.
Yeah,
okay,
sorry.
we miss the L.
Now FL is mu to the k harmonic, right?
To the K, yes.
Right? This does have period k, and this has distribution n steps of mu to the k. So each one of these converges almost surely, right? To
K is fixed or?
I want to see this as a sub. I mean, okay. So let's be careful. You guys can help me. I mean, instead of looking at the notes, you guys can help me. So let's see if we can do it. So we know, what do we know? We know that f. When I take this is the functions that I know work nicely, right? And then I can put in an x k n plus l. Right? This is the functions that why did I want to do? Yeah. So this thing is a subsequence of just ft xt, right? And those we know, we took L to be the 1a to be the limit of these things. So this converges almost surely to the indicator of A. But not only that, this is equal to the same as I can put just an L here. This is important. Okay? I can write FL x kn plus L.
Now L is fixed, right?
So now, yeah, this is true for every fixed L.
And is K fixed? Like what goes to infinity, N or K?
N.
K is also fixed.
Yes. K was a special number. Okay? So this is true for every L. Okay? Now, what do I want to say? I want to say that basically I can relate this to and this can almost surely what? Px almost surely for every x. Okay? But what does this mean? I can also look at Px. So I'm looking at the limit f L x k n plus k equals indicator A. So I'm looking at the probability of this event.
You mean Kn plus L or Kn plus
K n
K?
plus k. I just want a little bit more to do. Okay.
This is true for every element.
Let me write it differently. This is k plus nk, okay, or kn. I just want some k in the beginning here. You'll see in a second why. And this is from some x. Okay, so for any x, okay, I can ask for the probability of this event. Could be 0, could be 1, could be half. I don't know what it is. Let's see what it is. Well, I know what to do if this was L. Okay, no problem. First condition on the first k minus L steps being y, conditioned on k minus L, at time k minus L being at y, the rest starts at y and does L plus kn steps.
Py.
So using the Markov property, this is Py, right? Because this limit only looks at the end, so it doesn't care about this. Once I condition on this event, the distribution of the rest is exactly, looks like an xk, an xl plus kn starting from y. So you start from y and you get f l x l plus kn converges to, and you're asking for the probability that this actually converges.
This is 1.
This is 1. because it's true for any y, and then the sum over the y is giving me a 1.
Why can't you just say that comes from what's
Because it said the variable L strictly less than K.
yes, but if you take L equals 0 and N, you replace N with N plus 1, you get the same thing. K plus Kn is just K times N.
For L equals 0, this is trivial.
Oh, yes.
For L equals 1, I knew the convergence when I had
So this is
1 plus Kn, but I wanted to get
okay.
just 0 plus Kn, which was, so I gave myself an extra K, that's nothing. And the extra K was able to split it into that and move maybe to a different starting point. And that still gives you, because it's almost surely, so I don't care, you know. Waste a few steps, still get almost surely. Okay? So what we proved now is that these always converge, no matter what time, what L I take and what and the subsequence Kn, right? So what we proved is that this converges. So we just proved that G of x Kn, I could have done it with Kn plus L. You could play the game, right? It doesn't matter which period you take, but we proved that this converges almost surely, Px almost surely, for every x, it converges Px almost surely as n goes to infinity to the indicator of A. Because Gxkn is equal to the average of Fl at xkn, each one of these we showed converges almost surely to the indicator. So the average converges to the indicator. It's another reason to take the average. If I had the sum, it would converge to k times the indicator. Okay.
Then the event is where it equals 1, which is I measure.
And exactly now, but this converges almost surely to 1a, but it's also a subsequence of that one. So it also converges Px almost surely, and then goes to infinity to L. Right? So what does this mean? This means the probability that L is equal to 1a is 1. Okay? And now we take B to be the event L equals 1. Now L is I measurable, so this is invariant. L is I measurable as a limit of a function and not of a space-time function, right? And we know that this is, so we know that the symmetric difference between B and A is exactly when L does not equal 1a, right? So this is 0. Okay, so this completes the proof. So, but I hope you see that where was the obstruction? The obstruction was the period. Okay. Good. So this proves, let me recap, because I think tomorrow I'll just talk about Fazer Motz maybe. Fazer Motz. כמו שהמטוסים מפזרים. להסיח את דעתכם.
כל בעיניים.
I'll give maybe an overview of what's done, maybe open questions, things like this. But let's recap what we just did. We proved that every time you have a trivial invariant sigma algebra, you have a tail sigma algebra. But this is equivalent to having 0 entropy. So we proved that the 0 entropy is equivalent to having a trivial and sigma invariant sigma algebra, and a tail sigma algebra, and having no non-constant bounded harmonic functions. So these are all equivalent conditions. Okay?
תודה.